Welcome back. In this segment, we're going to be talking about thinking, language, and intelligence in our text. That would be Chapter 8. So the main topics, thinking, that seems like it speaks for itself, but there's a lot of detail to talk about with regard to how we think and make decisions. Language, we're going to talk about how we use language, how language is composed, stuff like that, a little bit about bilingualism. And then we'll talk about intelligence, how it's measured, how it's defined, how it is transmitted from one generation to the next. Okay, so let's get started with thinking. So the topics we're going to cover in this section of the chapter is concepts, problem solving, and animal cognition. So let's jump in and talk about concepts. I happen to be recording this in early winter, and this picture looks very inviting to me. It evokes certain concepts that we carry in our minds. Now, each of us has different concepts that are being triggered by this picture. Some of you might be thinking about the concept of vacation and relaxation, or some of you might be thinking about this is what it looks like outside your window, depending on where you live in the country. You might be thinking about the weather, whether it's warm in this picture or if it's humid in this picture. There's a lot of different kinds of things that kind of come to mind that are more conceptual level and less about concrete. Oh, look, there's a lounge chair. You're probably not thinking those thoughts. It's probably instead of evoking sort of feelings or hard to pin down concepts. Concepts are defined as a mental grouping of similar objects, events, states, ideas, people, anything that you could group together and sort of have similar reactions to or treat as if they're basically the same. So we don't even have to know where this picture was taken. It's showing us that it's a beach. We have a lounge chair that oftentimes represents relaxing or tanning. And so that can evoke in your mind your associations with these kinds of things. So if you want to remember back to when we were talking about schemas, Piaget's concept of schemas, his definition of a schema sounds a whole lot like this definition of a concept that I've just provided right now. It would be fine with me at the introductory level if you kind of lump those two things together, that concepts and schemas are roughly equivalent. Now, if you were my master's student studying cognition, I'd be like, okay, we got to get into some detail and show you why these things are separate. But at an introductory level, I think that's a pretty good comparison to make. Concepts are a lot like schemas because the idea is very similar, that you develop your own concepts based on your own experience in the world, right? Like this is your unique way of making sense of the world, just like a schema is. Now, a prototype is the best example that you can generate of a concept. I Googled the word prototype and found, prototype cars and other kinds of things. I found this nice GIF of apparently this prototype of a robot that kind of looks like he's dancing to me. He's kind of got that chicken quality where he can keep his head basically still even though his body's moving around. Anyway, so this is this robot maker's or this team's best example of this concept that they have of a four-legged robotic creature with, a long neck and a gripper on the end of it, right? So a lot of times we carry around with us a best example of the concepts that we have in our minds. So let me give you an example using the concept of chair. So chair is typically a concrete item, but the truth is it's kind of a concept because we use the word chair to refer to things that you can sit on. So technically, everything pictured could serve as a chair. I don't know about you, but my prototypical chair is the one on the center bottom. Like if you asked me to draw a picture of a chair and you gave me no other cues, I would draw something that looks like the item on the bottom middle. I would acknowledge I could sit on a fence and treat it as a chair. I could sit on a swing and treat it as a chair, but those aren't my prototype. My prototype is it's four-legged, it has a flat surface, it has a back that I can lean on. It's portable. For me, that's an important component of a chair. I would have a different name for something that is bolted to the floor. I might call that something else. So the things that go into your prototype of the concept of chair may differ from mine. You might be agreeing with what I'm saying. You're like, yeah, maybe that's a good one. Maybe you would have generated different description, right? Because based on your experience with a chair, your experience with sitting on things, you might have a slightly different prototype, like what a perfect example of that concept would be. So I think they all fit the chair concept, but one is more likely to be the prototype of the chair. Okay, I wanted to say one more thing about prototypes, by the way. One of the ways that we know that people have prototypes for their concepts is that they will be faster at recognizing their prototypical example of a concept than they will be at recognizing a member of the concept that's not prototypical. So, for example, if I asked you, is a robin a bird? You'd be a lot quicker at recognizing that a robin is a bird than you would be at recognizing that a penguin is a bird. There'd be a millisecond or more difference in your reaction time as your brain is going through the concept of bird and is a penguin a bird. And part of that might be because most of us learn what a bird is sort of from the time we're little. It flies, it has feathers, it might chirp, lay eggs, make a nest. You know, we learn these things about birds. And it's sometime, for most of us, it's sometime later that we find out that they can swim underwater, like a penguin can, that they make a nest out of rocks, that their wings they don't fly, they swim, that what looks like skin on them is actually feathers. That looks like skin on a penguin when it's wet. Those kinds of things, it takes us longer because it's not a prototypical member of the category. It also takes people longer to recognize that an ostrich is a bird because it doesn't do a lot of the normal things. I've heard people say that ducks aren't birds. And it's like, how is a duck not a bird, right? But they're like, wait, a duck's not a bird. Chicken's not a bird. Well, yeah, it is. Of course it is. But because it doesn't fit their prototype, sometimes people think, no, it's not a member of the class. It's not a member of the concept. So the closer an example is to our prototype, the more likely we are to correctly recognize that it is a member of the prototype. All right. So let's talk about how we solve problems. One way that we can solve a problem is through an algorithm. You might have heard this term in your math class, so you might already be familiar with this concept of an algorithm. You might have learned it in a computer science class where you were taught to write algorithms to make the computer run what you want it to do. So you might already know this word. Algorithms are step-by-step problem-solving strategies. So let's say your problem is that you're at a grocery store where you've never shopped before and you need to find some apple juice. Now, algorithmically, you might say, I'm going to ask the checkout counter if they have a map of the store. Now, I didn't even know this was a thing until I was watching an old show called Extreme Couponing, and they said stores have maps. And if you want to be an efficient couponer, apparently you need to know exactly where you're going and not waste any time. So now that I know that there are maps, I realized, well, that would be an algorithmic strategy for finding something. You might use a different algorithm called find a person who works there and ask them where the apple juice is. That's another algorithm. The thing about algorithms is that they can be a little time consuming. Going and asking for a map, going and asking for help. That can be a little time consuming. So a lot of times we instead rely on heuristics. Heuristics are sort of rule of thumb strategies. So we do something like, well, based on my experience with grocery stores, I know that they tend to put all the beverages together. And I'm looking for a shelf-stable kind of apple juice that doesn't need to be refrigerated. So I'm going to go walk along the ends of the aisles, looking down the aisles, and if I see any kind of juice or beverage, I'm going to go check that aisle, see if my apple juice is with that. If I know that what I'm looking for needs to be refrigerated, of course, now I'm going to go and look in the refrigerated section where I know they're likely to be kept. If I know that I like a type of apple juice that's, fresh squeezed or something, maybe I'll look closer to the produce section because I know a lot of stores keep that kind of juice there, right? Like you just sort of use your logic based on your experience with what stores tend to do. And this may be a little bit fraught with error. You might wander around aimlessly for a while trying to figure out where this store has placed their beverages or where apple juice is relative to other beverages. But a lot of times it can be a really quick solution. If you hit on the right solution right off, because your logic and this store's logic match up, you can be done really quick. The last method for solving a problem is called insight, and it's kind of tough to do this on demand, but the idea is suddenly the pattern comes to you. Okay, I can see that the refrigerated sections are towards the back, the produce is on the right-hand side, and I see this aisle with water on the end. I'll bet the beverages are down there. Like this sudden insight. Oh, I see the theme. Okay, so now I can set up my plan. Insight's kind of hard to do on purpose, though. A lot of times insight just sort of pops into our heads. So let me give you the individual definitions for each of these strategies. So algorithms are these step-by-step strategies where you, just like with a math problem or writing a program for a computer, you know that you have to do things in a certain order. The nice thing about an algorithm is if you follow the procedure correctly, you will correctly solve the problem. So it ensures a good solution. The problem is we oftentimes don't want to waste our time doing the steps that are required to follow the algorithm. And so a lot of times we don't use algorithms. Instead, we use heuristics. Like I said, this is a rule of thumb strategy. It's based on our experiences. It's not necessarily based on a step-by-step process. Instead, it's using our logic to sort of dive into the middle of the problem. We like them because they're quicker than algorithms, and we don't mind that sometimes we make errors when we're trying to do a heuristic approach. We say, well, it was a risk we're willing to take, right? So maybe I use my heuristic, I check all the places where beverages would be, I've checked the produce section, I'm like, okay, that's ridiculous, I'm going to go ask somebody, and I go back to an algorithm. Where's your apple juice? So it's quicker when you're right, when your logic makes sense. It can be error prone, though, when you do it wrong. The thing about insight is that it's usually done without intent. It's like that light bulb going on, and you suddenly realize the pattern. You suddenly realize the solution. So you can't do it on purpose a lot of the times. So insight is great when it comes to you after you've had a good night's sleep, or when you've been working on the problem and then suddenly you take a break, and then suddenly while you're on your break, you're like, oh, wait, I know what the solution to this problem is. It can be really handy if you've been stuck using one of the other two methods and couldn't come up with a solution, but it's really tough to do on purpose. All right, let's solve a problem. All right, so exactly at sunrise one morning, a Buddhist monk set out to climb a tall mountain. The narrow path was not more than a foot or two wide, and it wound around the mountain to a beautiful glittering temple at the mountain peak. The monk climbed the path at varying rates of speed. He stopped many times to rest and to eat the fruit he carried with him. He reached the temple just before sunset. At the temple, he fasted and meditated for several days. Then he began his journey back along the same path, starting at sunrise and walking as before at variable speeds with many stops along the way. However, his average speed going down the hill was greater than his average climbing speed. Okay, so that's your setup, and here's your problem. Prove that there must be a spot along the path that the monk will pass on both trips at exactly the same time of day. All right, so you might want to pause me if you really want to think about this and try and figure out the solution to the problem. I will tell you that there are at least two solutions that I know of that will assure us the ability to prove that the monk was at a particular spot, that he must have been at a particular spot at exactly the same time of day on both trips. Now, I almost said something that is an incorrect approach to this problem. Do not try and find the spot where the monk must have been. Try and prove that there must be a spot somewhere on that mountain where that monk was at the same time on both trips. All right, you can pause me if you want to try and solve it. Assuming that you've tried to solve it, you came back, or you're like, oh, no way am I going to try that problem. Let's forge ahead. So what can we do to prove that there must be a spot along the mountain where the monk was at the same time of day on both trips? Well, let's get algorithmic. Ooh, this looks like math. So we draw an X and Y axis. There's not much detail in that story, is there? So on the X-axis I put time, and really all we know is dawn and dusk, right? Sunrise and sunset. That's all we really know as far as time. And then I put altitude on the Y-axis, and all we know is bottom of the mountain, top of the mountain. We don't know anything else about positioning on the mountain. So with these minimal details, we can still prove that there must be a spot where he was at the same time of day on both trips. So let's say he left at dawn, he gained altitude across the day, and at dusk he arrived at the top. We know he took breaks, and there should be some flat periods where time is passing and he's not gaining altitude, but I didn't bother making a jaggedy line. We'll just let the straight line work as a stand-in for the details. Okay, so that's his trip up the mountain. Then he comes back down the mountain. Now we know he traveled faster on the way down. This line maybe should be steeper or something. Those details don't really matter for the proving of a spot. Those details matter if you're trying to use heuristics and you're saying things like, well, since he traveled faster on the way down, he was probably closer to the bottom when he would have crossed himself. I don't know, maybe he had lunch in a particular spot and spent time, and he had lunch at the same place on the way down. Yeah, maybe it's the lunch spot, something like that. Those are heuristics. And they don't really allow you to prove that there must be a spot. There's no reason why he would have to have lunch in the same spot both trips. There's no reason why he'd have to eat lunch at the same time on both trips. So we can't prove it using that kind of logic, those kind of heuristic solutions. We have to do an algorithm. So I've drawn proof right here. Here we have objective proof that he was at the same, that there is a spot somewhere on the mountain where he would have been at the same time on both trips. The fact that these two lines cross, and they'd have to cross, no matter how I draw them, there's no way, no matter how accurately I draw the lines so that he's taking breaks, and I make the one on the way down steeper, and I do all the things and make it as specific as I can be, there's nothing you can do but cross those lines. They have to cross. That point is the intersection of time and altitude, right? That spot shows us that at some point these lines have to cross, and they'd have to cross at some point where he would be at the same time both trips. All right, let's get even more concrete. I found a picture of a monk climbing a mountain on the internet. So you literally can find anything in Google Images. But actually you can't literally find anything. I lied, because I found a picture from the rear of a monk climbing a mountain. I could not find one of him coming down. So watch my sad little attempt to make him come back down. So here we have him climbing. He's at some point on the mountain. You imagine let's make it this concrete. Let's say instead of one monk going up on 2 different days, and we're trying to do it in this sort of, hold it in our heads logical way. Let's think instead about one monk starting at the bottom and one monk starting at the top of the mountain. And they're taking the same trail. They're going to have to pass each other, and that's what I try to make happen here. Oh, there's the monk coming down the hill. So the fact that 2 individuals, one starting at the top and one starting at the bottom, would have to pass each other reminds us that, yeah, monk from the ascent and monk from the descent would have to, pass each other, right? They'd have to have been at the same spot someplace along this mountain. Now, I don't know where it is, because, we would have to have more detail about all the things. To say sunrise and sunset, we could get really super specific and say we don't even know what time sunrise is from one day to the next, because it changes every day. So we can't be perfect and know exactly where we don't even know what mountain he's on. So all I can say is that on a mountain with one path, he'd have to cross the same spot at the same time at some point on that mountain. Algorithm's the only way to do it. Now, let's say that I gave you this challenge. We've got a nice, scrambled word, and I ask you to unscramble it. We're clearing our heads by doing something much easier than that monk example. Hopefully you scrambled it almost immediately. If you used an algorithm to unscramble those words, you would have to try all 782,200 possible combinations of these letters and then decide which one is probably the most likely to be the word. I'm going to guess you didn't do that in solving this problem. I'm going to guess that when you saw that scrambled word, within a couple of seconds you recognized what it must be, because you used a heuristic. Your brain knows there's no such word in English that has two Y's in a row. There's no such word that has certain other letters in a row, right? So you can throw all that junk out. But probably even more powerful was that you were able to use context. You're already thinking about psychology. We're in like that part of your neural network where you're thinking about psychology. So hopefully the word psychology popped out really easily for you, because your brain doesn't have to go through every possible algorithmic combination like a computer would have to do. Instead, you can use context. That's one of the things that's made modern AI so smart, is that they've taught AI to use heuristics, to use context. It's almost frightening sometimes when you start to type things into Google and it's like, I think I know what you're asking about, and it'll fill it in. And it's like, I was asking about that. I like it. It's horrifying, yet I like it, that I can have been watching a particular video and I want to know more about it. I start to type in details and it already knows what I'm talking about because it knows what video I just watched. It's creepy. I don't like it. I want to stop using it, but I can't. It's the worst. But so you use context. You use your experience. And so you can solve problems way faster than a computer could, because you can jump to the end. So talking about jumping to the end is a good time to say we make some mistakes. There are some thinking strategies that we tend to use that make us less effective problem solvers than we could be if we didn't leap to conclusions. So the first one is what we call confirmation bias. We have a tendency to seek information which supports our beliefs and to disregard contradictory evidence. We don't want to hear things that would show us that we are wrong. We want to hear things that show us that we're right. So we look around in the environment for more evidence that we're correct. This is why arguing on the internet is so stupid and hopeless. If you do it, I'm sorry, I didn't mean to imply anything, but it is hopeless. Because we can all find evidence that'll back our side, and we can always try and refute somebody else's evidence by providing more evidence that supports our side. And we don't want to hear their evidence. We don't really read it. We don't really want to hear it. We just want to tell them that they're wrong and provide the evidence that we have, that we're right. We want to be right. That's the confirmation bias. So in our natural tendency, the way that we think about things, we try and figure out, how would I know if I'm right? And we say, well, if I'm right, then this fact would confirm my theory, so I need to look for this fact. That's my job, is to look for facts that would support my belief. That's our natural tendency. That's normal logical thinking. In science, we actually suspend that natural tendency and instead adopt a scientific attitude, which is where we say to ourselves, if my hypothesis is correct, my job is to try and disprove it. If I fail to disprove it, then the hypothesis is at least still in the running. I can't say it's right. I can never prove anything. All I can say is that my job is to look for evidence that would disprove what I believe. So if I'm right, then fact D would disprove or at least disconfirm my theory, so I need to look for fact D. That's my job as a scientist, is to look for the evidence that I'm wrong. If my hypothesis stands up to all my attempts to disprove it, then I could say, well, at least I'm not wrong yet. I don't ever say I'm right as a scientist. A scientist should not say that they're right. A scientist should never say the science is settled. A scientist should never tell you, if you are questioning something, then you are a denier. There should never be those phrases coming from a scientist, because scientists welcome attempts to disprove the theory. That's their job. A scientist should never look for evidence that supports what they believe. If they're doing that, it's called junk science, and it shouldn't be trusted. Let's do a little test. All right, so we have 4 cards in front of us. You're seeing one side of the cards, right? So you're seeing an A, a D, a 6, and a 7. Each of those cards on the reverse has the opposite kind of character on it. So if you're seeing a letter right now, on the back is a number. If you're seeing a number right now, on the back is a letter. In fact, the whole universe of possible things that can exist are A's, D's, 6s, and 7s. That's it. That's all that can be on these cards. So on the back of the A is a 6 or a 7. On the back of the D, a 6 or a 7. On the back of the 6, an A or a D. On the back of a 7, A and a D. A or a D. Each of these cards is an independent event. So if there's a 6 on the back of the A, that doesn't tell us anything about what's on the back of the D. If there's an A on the back of the 6, it doesn't tell us anything about what's on the back of the 7. So each card is an independent event. Okay, so now that you know how the cards are constructed, here is your problem. Which 2 cards would you turn over to test the hypothesis that if a card has a vowel on one side, then it has an odd number on the other side? So you can only turn over 2 cards. Which 2 cards would help you to test the hypothesis? Ooh, I used that science word, right? So try and think scientifically. Which 2 cards would you turn over to test the hypothesis that if a card has a vowel on one side, then it has an odd number on the other side? Okay. Usually I get my students to vote. It usually goes in a very predictable pattern. So I'm going to assume you're thinking similar thoughts. There's always a couple of quiet people who've got a different idea. It's usually the ones who are feeling really super confident about their answer they'll share. Most people want to flip the A, and it makes a lot of sense. Flipping the A has the possibility of supporting our hypothesis. We might flip it over and find that there's a 7 on the back, and we go, oh, so the hypothesis is still in the running. The thing that makes the A useful is that it could also refute the hypothesis. If we flip the A over and we find a 6, then our hypothesis has been disconfirmed, right? There's a card with a vowel on one side and it has a 6 on the other side, then it would disconfirm this hypothesis that it should have an odd number. So the A is really informative. Really, that's a useful card, but it is not the first card I would flip over. If I were actually testing the hypothesis, and let's pretend like this is a meaningful test question, right, like an actual study, I would want to go after the information that would have the best chance of showing me if I'm wrong. I want to go there first. So let's figure out which one that is. It's not the A. It's not the D. The D is only here for symmetry. Sometimes I'll have students say, well, what if you find a 7 on the back of the D? Then you'd have an odd number and it's not on the back of a vowel. But the hypothesis doesn't say anything about what needs to be on the other side of an odd number. It says what needs to be on the other side of a vowel. So the D is actually just a distractor. We don't need to flip it. We need to flip the 6. That's the first place I would go. Because all it can do is disconfirm the hypothesis. If I flip over the 6 and I find an A, then I have a vowel on one side and something other than an odd number on the other side. So I'd know I was wrong. There's no point in even bothering to flip over the A, which might have a 7 on the back. And then I'd think, well, wait a minute, is my hypothesis right or is it wrong? My hypothesis is wrong. There was a 6 with an A on the back of it. Now, if there's a 6 and there's a D on the back of it, that doesn't do anything about our hypothesis. So it would still be in the running. So if I flip over the 6 and I find a D, I'm going to go next to the A because it's the only other card that has a chance of showing me that I'm wrong. Most of my students want to flip over A and 7. 7's very attractive because if I flip over the 7 and I find an A, then I'm like, oh, look, hypothesis is correct. No, it's not. There's no chance that 7 could show you that you're wrong. If you find a D on the back of the 7, I already explained why that doesn't matter. So if I flip over the 7, I've just wasted my time. All it could do is show me I was right. And if I skip the 6, especially you're only given 2 cards to flip. If you skip the 6 in favor of flipping the 7, you might think you're right and you're wrong. The 6 would have shown you. So this is what I mean in science, that we have to look from the opposite angle than what we normally do in our everyday life. Like if you want to be objective, your job needs to be to look for evidence that you're wrong. It's hard to come up with a way of testing our beliefs so that we'd be able to show ourselves that we're wrong. It's hard. A lot of times we slip into, okay, so I don't believe what I'm reading. I don't believe what I found. Well, See now, because things are not as clear cut as flipping over cards and finding one kind of character on the back, right? Real life involves, well, do I believe this evidence that's telling me I'm wrong? It's tough. And so in our everyday life, we tend to look for evidence we're right, in large part because we don't really know how looking for evidence that we're wrong would actually manifest itself. Like, how would you even do it? So I'm not judging anybody for displaying confirmation bias. That's an everyday way of looking at the world. But if you're going to try and make arguments against people on the internet, looking for evidence that you're wrong is more helpful than trying to find evidence that they're wrong. That's why I don't argue on the internet. It's too much work. Rather write scientific papers with objective data. So, other problem-solving habits that make it more difficult for us to solve problems accurately. Mental set. We typically will get into sort of a expectation, right? That word set means expectation. So our brain is expecting, we have this mental expectation that the problem will be solved the same way similar problems have been solved. It doesn't even have to be the same problem, just similar problems. This is called the three-jug problem. I wonder why. So we have three jugs, A, B, and C. And on each trial, the participant is told that the jugs can hold differing amounts of water. So in problem 1, for example, we're told that jug A can hold 21 units of water, B can hold 127, and C can hold 3. And your job is to measure out 100 units of water. You're not allowed to estimate, try and just fill up B till it looks like about 100 units. You can't do that. You have to get exactly 100 units. So how would you do this? Well, people usually kind of struggle around with it, and then they ultimately figure out that the solution to the problem would be to fill B up till it's full. So we got 127 units in there. Pour 21 units into A, pour 3 units into C, empty C, and then 3 more units into C, and we will be left with 100 units in B. And so once the insight comes to the participant, they go, oh, I see how this works. And they have to figure out, I'm allowed to dump out C. I mean, I don't see a receptacle for dumping out C, but apparently magically we can do that. And so once they figure out the rules, they're like, oh, okay, I see how this works. And I've got a little drawing that shows you how it's done. Then they start figuring out, oh, look, now I've got A can hold 14, B can hold 46, C can hold 5, and I need 22. Okay, if I fill up 46, dump out 14, dump out 5, dump out 5, I'm 22. Hey, it works here too. Okay, I got the system. Okay, I've got the system. And they get really quick on like trials 3, 4, and 5. They're like, I've got the system. I know how to do this. Then it gets interesting when we get to trial 6. It actually works exactly the same way, right? You could do fill jug B, which can hold 49, dump 23 into A, 3 into C, 3 into C. That'll leave us with 20. But there's a faster strategy. You could fill A, dump 3 units into C, and you'll be left with 20. Like that would be faster. So the strategy that you've been using still works, but there's a newer, better strategy, right? And then when we get to 7, I forgot I showed you a picture of that too. When we get to 7, now we have to get 18 units, and jug A holds 15, jug B holds 39, jug C holds 3. The fastest way to get 18 would be to fill up A, pour it into B, fill up C, pour it into B, and we'll have 18, right? So the people who used the same strategy for trials 1 through 6, they didn't see the insight that there would be a faster way, oftentimes are completely stumped by what to do on trial 7. Because the original strategy doesn't work. And they're like, what do I do? What do I do? I don't know how to get there. And they're stumped. Whereas the people who on 6 recognized that there was another way to do it tended not to be stumped by 7. So we conclude from that if we get you into a mental set, sometimes it'll actually cause you to get stuck on a problem and not know how to solve it. You're stuck in your rut. You can't think of a new way to solve the problem. Which brings us to another variation on that same theme, fixation. You can't see the problem from a fresh perspective, and so you're stuck. You're fixed on trying what you had been trying. So a lot of times fixations occur because you were experiencing a mental set, right? Like, I've gotten used to solving problems like this. I can't think of a new way to do it. Now I'm displaying fixation. Fixation oftentimes can happen just because you were just confronted with a brand new problem, and you're like, I don't know even how to approach it because it doesn't look like anything I know how to do. It's like I'm stuck on thinking about it like this. Like, for example, participants were given 6 matchsticks, and they were told to form 4 equilateral triangles. And I think they were given a photograph of the matchsticks. They weren't given actual matchsticks. So they are asked, how can you arrange 6 matchsticks to form 4 equilateral triangles? And if you recall from math, equilateral just means all 3 sides are the same. So clearly, you need 1 matchstick for each side. Obviously, we're not going to break them or do something like that to try and get some kind of, they have to be equilateral, right? So you'd end up with unequal sides if you broke them. So they've got to be 1 matchstick per side, but how are you going to do that? And I've had some students suggest like making almost like a row of conjoined triangles so they could be sharing matchsticks, but if you draw that out, that doesn't work. And we always tend to come up with solutions that are 2-dimensional because I think we're kind of fixated on the fact that the matchsticks would have to be laying on the table. Like, how else would you do it? The solution requires like no gravity or something sticky to make this actually work, because we're in 3 dimensions here. So you would basically make a pyramid out of them. So you have 1 equilateral triangle on the table, and then you take the remaining 3 matchsticks and put them on each corner and bring them together, and you end up with 3 equilateral triangles making up the sides. But we weren't told we had glue or double-sided tape or something sticky. We weren't told we had that. So the fact that we were stuck, we were fixated on working out a solution that would work in real life, prevented us from being able to come up with a solution that, causes you to have to, think outside the box, outside of real life. You would need more materials to make this solution work, but on a piece of paper, you could sketch it out. There's no reason why you can't do it in a drawing, but we don't think about it like that because we're fixated on making it work in real life. This is another example of fixation. This is called the 9-dot problem, again, for obvious reasons. We're assigned to use 4 straight lines to connect the 9 dots. And the rules are you can't pick up your pencil, you can't backtrack over a line that you've already drawn. So you only get 4 straight lines, and you need to connect the 9 dots. So if you're like a lot of people, I'll use my arrow. I don't know if you guys can see it or not, but you'll go sort of around the outside making a spiral, but that takes 5. Sometimes people will do sort of like draw an S kind of strategy, and that also takes 5. It doesn't work. So then we go, well, it's impossible. Our fixation is that we have to stay within the dots, and we said the problem's impossible. It can't be done with only 4 lines. So let me draw the 4 lines here. Now you guys can see that I used just straight lines to do this. So I didn't pick my pencil up. But see how you have to go out past the dots to make this work? Most of us have had enough experience with dot-to-dot problems that the thought of going outside the dots doesn't even occur to us. We're like, wait, why would you give me dots and then tell me to go outside of them? The first time I ever saw this problem came in with the caption, sometimes you have to think outside the box. And I got to tell you what, that still didn't cause me to solve it. I was like, what? I kept doing all the things that would connect the dots. Nothing worked. That little hint didn't help me at all. Think outside the box. I'm trying. I can't think of anything. But they meant literally you got to go outside that box of those 9 dots to solve the problem. There's actually an even simpler, fewer than 4 line solution. But boy, you better have big dots if you're going to try and solve it with 3 lines. And you have to go way outside the dots to solve it. So a lot of times we get fixated on solving the problem, using our past experience, our strategies that have worked before. We're like, I'm going to do what I've done before. I've done dot-to-dot problems. That's how I'm going to solve this. And actually, there's a third solution that takes one line. And what you do is you fold the piece of paper so that part of each dot is showing. So you like fan fold the paper so that part of each dot is showing, and you draw one line through all the dots, touching each partially. I would never have solved that problem. The availability heuristic. In the availability heuristic, and I already told you what a heuristic is, right? It's a rule of thumb strategy that we use based on our previous experience. So in this one, we're going to estimate the likelihood of an event based on how easily it comes to mind, how available it is for us to retrieve from our memories. So, for example, in one study, they asked people in English, which is more common, K in the first position or K in the third position? And in the research, what they found is that people judged, that's the left part of the panel, people judged that K was the first letter more often than the third letter, than being the third letter. In reality, some poor grad student back in the day, this study was conducted in the 70s. In reality, this poor grad student had to go through the entire dictionary and find all the words that started with the letter K and then all the words that had K in the third position. And in reality, it's much more common to have a word with K in the third position. And if you think about it, it makes a lot of sense, right? There are a lot of K in the third position words, but they're harder to think of. You'd have to really look and think of them. And like one of my students generated irk as a K in the third position word. I'm like, of course, that's a terrific word. I was stuck in examples like make, take, bake, lake, fake, rake. And then I get off of that one and I go bike, hike, like. It's like get stuck in these rhymes of four-letter words that have K in the third position. And then I get stuck and couldn't think of it anymore. And it's easier to think of things like kiss, kill, kilo, kite. It's easier to think of words that start with the letter K. Maybe our lexicon is organized alphabetically or something in our mind. I don't know. But it's easier to think of words that start with the letter K and harder to think of ones that have K in the third position. So we think that words that start with the letter K are more common. Availability heuristic. All right, still on the thinking errors. Overconfidence, the tendency to be more confident than correct. Here's an overconfident cat. Oh, I'm going to get the birdie. That birdie looks like, yeah, you try it, kitty cat. I'll tear you apart. I hope the kitty cat thought better in the end. But we sometimes are overconfident. We think we know things that we don't actually know. And we oftentimes will really stubbornly stand behind our misunderstandings and really believe that we are correct, when in fact we're not. We won't accept other people's evidence, right, because we really think we're right. Belief perseverance is our tendency to hold on to beliefs even in the face of contrary evidence. You could see this working in concert with confirmation bias, right? Like even if we do find evidence that runs contrary to what we believe, we will stubbornly cling to what we already believe. That was a very well laid out rational point. But I will still hold to my emotional opinion based on no facts or evidence. That's belief perseverance. A lot of times, because we've known it for a long time, we feel like it's got to be true, and we will stubbornly cling to it. Stereotypes are based on belief perseverance. A lot of times, disagreements that we have over, politics or religion or other things we're not supposed to talk about in polite company, right? We think that if we've always known it, it has got to be true, right? That whatever it is that we've always known, we feel like it's got to be true. But it might just be that we're clinging to it because we assume it has to be true, and it doesn't have to be true. So we oftentimes are overconfident. We oftentimes stick to what we think we know, even in the face of evidence that we should switch our attitudes. So what about how the problem is set up? Framing. Sometimes we think incorrectly because we focus on the wrong part of the problem. Sometimes we're manipulated into thinking about the wrong part of the problem by marketing and stuff like that. Sometimes they want us to notice certain parts of the problem, so we won't notice the part that might not make us not want to buy their product or something. How the problem is set up. when we read the back of the package and see that condoms are 95% effective, we think, they seem reasonable, they seem safe, I'm willing to use them. I mean, what's the likelihood it will fail? Oh, 5%, that's nothing. 95%, I'm going to focus on 95% effectiveness. And by the way, they are very effective. They are the only method that prevents STIs. Sorry, that's my disclaimer. I teach human sexuality too. All right. But a lot of times we ignore the other part of the frame, right? 5% ineffective. If you ever watched Friends back in the day, I know it's on now too, but back in the day when Ross and Rachel got inadvertently pregnant, he says, but we used condoms. And she said, well, did you never notice on the back of the package that they're only 95% effective? And he's like, they should highlight that 5%. And he's kind of right? The framing is to put our mind on, look how effective they are, and they are very effective. And to take our mind off of the possibility that something could go wrong, right? That's a framing issue. So how we set up the problem, and I mentioned this way back when we were talking about marriage and divorce rates, and I said, let's reframe the problem, right? Instead of talking about, a 28% failure rate versus a 38% failure rate, let's look at 72% success rate. Right? Let's look at it the other way. Let's think about it on the positive side. You can reframe problems sometimes and recognize that you were thinking incorrectly about something, that you were ignoring the other part of the problem. Okay, so I'm going to take a break here, and we will come back in the next segment and talk about language structure, language and how we use it.